Participants, please be there in the meet. We'll start the session once the speaker will join.
Participants, please be there. We are starting our next same meeting link very shortly. Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Can I share my screen?
Sir, just wait for a minute.
Okay.
Is my screen visible, ma'am?
Yes, ma'am.
Yes, yes.
Shall I start?
No, ma'am, let me start the record.
Okay,
Just
okay,
wait.
sure.
Wait.
Okay, ma'am, sure.
Radhika, ma'am, present your screen and then start.
Yes, ma'am. Is my screen visible now?
Yes, yes, yes.
Shall I start?
Yes, ma'am.
A very warm and pleasant afternoon to one and all present here. We welcome you all to our 12th session of 6 days online ATAL FDP, that is Hybrid Computing Trends. I, Mrs. Radhika Pasgare, on behalf of Information Technology Department at AC Patil College of Engineering, welcomes Dr. Vamshi Krishna Sabbi Sir to the ATAL FDP on Next-Gen Computing, Advances in HPC and Quantum Technologies for Data-Driven Insights. We are pleased to introduce Dr. Vamshi Krishna Sabbi, a postdoctoral researcher at IIT Goa and adjunct engineer at CDAC Pune, specializing in high performance computing. He holds a PhD from Dr. APJ Abdul Kalam Technical University and has contributed significantly to India's national supercomputing mission. With expertise in parallel programming, GPU optimizations, and HPC systems, he has published over 25 research articles. Dr. Sabbi also mentors students and professionals in OpenMP, MPI, and CUDA programming. We welcome you, sir. Please accept our virtual token of respect.
Thank you.
Now I request Dr. Vamshi Krishna Sabbi, sir, to start the session. Over to you, sir.
Okay, thank you. Let me share my screen.
Yes, sir, please.
Uh, can you please confirm screen is visible to everyone?
Yes, sir.
Yes.
Yes, sir. Yes.
Thank you. So I first of all I welcome everybody to this ATAL FDP program. So in this program, because there's only 1.5 hour is there, I know this kind of content cannot be covered. So I will bit go fast, but I will try to always compress myself during the program. In this course, I'm going to cover the hybrid computing and what is hybrid computing and its trend, as well as I will cover a GPU server board and its architecture, some concept of vector pipelining, SIMD and SIMT comparison, and how we do the compute capacity calculation, memory bandwidth, etc. And last, there will be a question and answer session. So any participants, we can ask their doubts and their questions. I will try my best to answer those queries. So first thing is, what is hybrid computing? So whenever I'm talk about the word hybrid, so we know that the integration of so many things. Hybrid means it is a mixing of so many things, right? So similarly, these days, if we see these days, there are multiple computing paradigms are available, and we use it daily in our day-to-day activity or any scientific activity as well. Just like we are talking about the cloud computing cloud computing infrastructure, that is a kind of computing paradigm, and we are using high performance computing clusters or high performance computing infrastructure. That is also a on premises infrastructure. And similarly, we are talking about the some clusters we are designed specifically with some specific software stack for the AI ML workload, and similarly for quantum computing. So when we wanted to use all this infrastructure to solve some problem together, so that sort of understanding, that sort of architectures gives the like hybrid computing infrastructure. So before moving to the hybrid computing, so what's the paths we have gone through in so many years, almost 75 years of computing world. So you know that in early computing era, that was started in way back in 1950s to 1980s. So we were talking about the mainframe supercomputers, and this mainframe supercomputers were specially designed machines to solve the scientific computations, and they were not available in the off the shelf. So every organization has to make a special order for the design of such machines. So Cray, that time the Cray was an organization, they used to design such big machines. And because they are a specific machines, so they were not easily available. So there's a high cost is involved, and limited flexibility was involved on those machines. And obviously there was a lacking of distributed and parallel computing capabilities. So first of all, it is defined in a four walls. Only those who have access of that, and what are the models or programming concept they have developed, only those who have access of that, they can only use that. So there was some obvious limitations was present in a earlier computing era. After that, we move to some distributed computing. So in a distributed computing, we are always talking about the uh, cluster. We call it cluster. So what we are trying to do, that instead of mainframe computer, we are integrated the a lot of commodity based computing infrastructures like servers, and they are connected with some high speed interconnect. They have developed some special topologies to that, to connect all the machines. So that tradition has grown, and till date that was being used for any scientific computations using parallel programming or parallel programming paradigms. So obviously this has some challenges, like we are it is always difficult to handle or manage the one machine, and we are talking about the large number of machines are connected together, and each machine have their own software, operating systems and some software stack, and we have to make them the proper communication channels at hardware level, at software level, so that they could work work in together. So that complex setup and management was a tedious task, and it was highly challenging in those days. Now in around 2000 there is another era, another revolution, you can say, that the introduction of cloud computing infrastructure was came into the action. And you know that even today we are using Azure, Amazon, and many parallel platforms are available in a cloud infrastructure. So what happened, impact, what the impact it has done. So there is again one challenge. Cloud was being used widely these days, just like we are using Google services and other Azure services as well. And we are, earlier days we used to deploy our web servers on premises or in-house servers, but these days we are directly deploying all those on a cloud infrastructure by hiring the resources. So that is a very important computing environment. But again, the cloud computing environment is not as efficient as for complex scientific computation, because of the we are thinking it of it's alternative for the on-premises cluster, but it is not, in my view, in my personal understanding. It is bit difficult because we don't have an idea which resources will be allocated to you and how they will be communicate with each other. So high performance infrastructure are tightly coupled, and they are bare metal kind of infrastructure, so they are highly fastest infrastructure. Then because of cloud computing and many infrastructure edge computing we are talk about, so all this uh, different computing infrastructures was around us, for obviously for different purpose, different operations to they support and they cater. So rise of you can say the people start thinking toward the hybrid models. Why we cannot? Because for cloud computing you can scale the things very easily, but in on-premises computing infrastructure you cannot scale the things. um, Cloud computing infrastructure we can use a post-processing kind of thing, we can do the business intelligence that can be used, but for pre-processing and the actual computations, especially in AI, if I talk about AI models, we have to train the models, and training is a very compute intensive and as well as sometimes memory intensive task as well. So that scenario, this on premises cannot be sorry cloud infrastructure cannot be as efficient. So there are different categories, different purpose for every computing infrastructure. So people start talking about why we cannot integrate that. So when we are integrating the cloud infrastructure, edge computing, and high performance computing, so that is giving a sense of hybrid model. So we started calling it a hybrid computing infrastructure. So that was a beginning, and what we are thinking today. So we are thinking today is like in modern hardware computing, it's a game of tool, because if you see that processors may be same, internets may be same, connection of these devices may be same, a little bit here and there. Some will be high speed, some will be low speed, some memory bandwidths will be high and low based on the requirement obviously. But main thing is that the how it has to be integrated. Suppose I am using the slum, we use the slum in on premises infrastructure, and Kubernetes, they are very much popular on cloud infrastructure. So thing is that how we can integrate these two, so without developing any new software stack and any new changes in our infrastructure. So such kind of challenges are always there. So the tools are available, and these tools, we have some API calls that has been developed to integrate with each other. So that is basically helping, rather than we are totally working on hardware. So people are working more toward on the software things, so that they could establish the proper connection between the various infrastructure. for effective utilization of these resources for the solving particular complex task. Now, what's that the future directions of hybrid computing? So there are things like AI driven workflow we are always talk about. So in if I tell you my experience in NSM infrastructure, so there are various clusters and people, those who are researchers and academicians, those who are working in various scientific domain, they are submitting their application, their jobs on a cluster, and resources is not free. Sometimes resources is free, but required resources is not available. Obviously some challenges are always there. So people always think about why we cannot divide the workload division can be done based on the AI for the uh, means to improve the performance, to improve the operation of the entire cluster. The thing is that like I will just take a small example here. Suppose there is a one application, we call it computational fluid dynamics, that is used for car crashing, airplane design, airplane crashing, so many things. So any 100 users are using this application and they are running their job, they are changing some their input parameters and they are running their job, and they are getting failed or sometimes they are getting success. So some stuck in some environment, my AI driven means models can identify those which resources is suitable for this workload, how many resources is required to compute this job very quickly. Suppose generally it takes 4 hours, by adding one more resources it can be done in 1 hour. So such kind of decision a human cannot take because they are only dealing with the input file. So if this kind of automations can be driven by some AI models, then it will be more helpful. Just think about, by adding one or two resources that are available, if my task completion time is reduced from 5 to 6 hours to 1 hour or 2 hour, there will be a gap of 3 to 4 hours, and this 4 hours resources will be free and it will be allocated to the other users. So such kind of activities being done. And exascale computing is also the solution. We know that the we are India also working toward this direction, and already some exascale machines are there. And another focus is on the sustainability focus. Okay, so they want to make efficient models so that they can reduce the carbon footprint. So you know that whenever we are using such resources, so a lot of energy and carbon is being produced somewhere. Now, okay, so I will just focus on this part. So I will just highlight this thing. So any environment, any different environment, if we talk about, so these are the main uh, computing resources that is used to solve any problem or used to do the any computations. And if I'm talking about the cloud, if I'm talking about the quantum, if I'm talking about the edge computing, if I'm talking about the HPC or high performance clusters, so these are the main computing devices that are used here. And over that, the some software stacks are there. So there always a hybrid computing versus heterogeneous computing. So as you know that some computing resources are same in every paradigm. Only things some here and there, some changes may be there, but 90% things are same. But what's the difference between hybrid computing and heterogeneous computing? This is another term. So I will more focus on heterogeneous computing also here. So what is happening? We know that hybrid computing, we are just integrating the different paradigms, uh, HPC, cloud, and computing. When I'm talking about the heterogeneous computing, so we use that different. We will always focus on the different types of processor architectures, CPU, GPU, and FPGA, and all things can be in one in the same machine or same system. So what will be the focus? Integration of distinct environment resources that I already discussed. So in heterogeneous computing, uh, my our object will be how the we developed the means just think about. I will explain it like this: CPU has their own architecture, GPU has their own architecture, and both is developed by different vendors and different architectures they support. So same compiler that is used for the CPU will not work for the GPU. So how to establish the collaboration with these two hardware devices so that we could optimize the performance. So such kind of things we have to take care. And next important thing that always focus on here is the programming models. This was as a developer point of view, it is very much important. So if I'm talking about the hybrid computing, so we are always talking about the orchestration because there are, HPC have their own orchestration, cloud has their own orchestration. So we want to develop some unified orchestration for the and for the different computing paradigms. But when I'm talking about the heterogeneous kind of thing, so you can see we have to think about uh, this thing just like various programming models, just like if I'm talking about the CUDA NVIDIA GPU, so I have to learn about the CUDA programming model. Or this OpenCL is a kind of portable model. And if I'm using SYCL, basically SYCL has a various variant. So if you are Intel SYCL, you can use SYCL. Also have one specialty like it the we write a program in a SYCL that will work on CPU as well as GPU. That's a unified programming approach. So such kind of development is happening across in scientific communities. So these are the I'm just because of time constraint I'm focusing on the important aspects, and remaining you can study and you can understand. So these are the key components. So I already highlighted that these are key components here. So next one is what are the trends in high performance computing. So the first emerging trend is the heterogeneous architecture. So we always have to solve this problem. Second one is a cloud infrastructure problem. So I already mentioned that at software level, the work is to be done. It is already being done. Only thing is how we can make it more efficient. Next one, these days we are talking about the HPC AI convergence. So because AI workload is very much different from the scientific workload, but AI, because of the huge data, uh, there is a need of HPC for training the model. But I would like to add one more thing here. You can participant can study some article on it that is available. Um, Big data, AI, and HPC convergence. So so why we are talking about the AI HPC convergence? That is only because of the big data, availability of data, and all this data has been pre-processed, clean, everything is done, and they are stored in various data lakes, data warehouse, and now data buckets is also created. So so AI people wanted to use those data for develop the models for their work of domain. So it means thing is that all these three things work together, work need to work together. And AI, the big data has a different stack, and AI has a different stack, and HPC has a different stack. So if you talk about the big data, people always earlier people were used to talk about the Hadoop, but these days we are talk about the Spark. And similarly, when we are talking about the AI, so we used to talk about the GPU, multiple GPU distribution, and they also need um, multiple what I say distributed programming model. So HPC is well suitable for that. So how we can do HPC? When I'm talking about the HPC use a parallel file system. So we have to again think about how I can process the data using the parallel file system. Whether I can use Spark, can I integrate my Spark with the scheduler, that is used in a means storage file system. Luster we use in HPC system. So how we can integrate that, and how the data can be processed, means we can read and write the data from the database in a distributed manner. So this is a hybrid model, and obviously different architectures are being used for this. So that is the reason more work is going toward the development of software ecosystem. So hybrid ecosystems, we need a hybrid ecosystem, but we are always looking for is a user friendly system. Means suppose you might have a GPU, NVIDIA GPU, that should work for NVIDIA, support the NVIDIA GPU. In case you have an Intel GPU, that should be the Intel, support the Intel GPU. And if you're talking about the distributed using OpenMP or MPI, your tools must also uh, support this kind of infrastructure, shared or means what I call shared memory model and distributed memory model. So the challenges in hybrid computing, the programming complexity and interoperability, that is obvious thing, just I discussed. Second one is a data movement bottleneck. So as obviously HPC, we use parallel file system, and we use those object storage system. So they are really much faster than the other storage system that may be used in AI and big data. So we have to be, that could be a one kind of bottlenecks. uh, Next, we have to think about hardware software compatibility, that is to be checked. And at last, when everything is fine, so we have to think about the resource scheduling. So these are the still a biggest challenge in hybrid computing environment, and industries and communities working toward this direction. So now I will give the idea about the CPU system and GPU system. I mean, what I will call it as a heterogeneous scenario. So, what is a server board? We know that. I will highlight here is that, just one second, my pointer is not working. Yeah. So we in any computing environment, we call it as a CPU compute and GPU compute, or some people call it as a CPU server or GPU enabled server, GPU ready server. There are different names they have given, but I will just discuss about how they differ from each other. So you can see there is a motherboard, and in any motherboard there are compute unit. The first primary compute unit is your CPU. In motherboard, I have mentioned two CPU here, CPU 0 and CPU 1. So server board, it depends, might have one CPU socket where you can place one CPU, and server boards may be available with dual socket, so where you can place two CPU, and similarly for octa socket or quad socket servers are available. So accordingly, that is totally based on your computing needs and the money in your pocket. After that, there is another thing is RAM is there, and IO hubs. That IO hubs is basically help to interface the external devices for this motherboard. And storage system, small storage, means we call it as a hard disk and SSD, that can be there. So there are two types of what I call infrastructure: stateless and stateful. So it is again the need. Suppose if you are using the stateful, then your storage system is required. If you are using the stateless infrastructure, then a storage system is not required. You have to increase the RAM size in that scenario, and your operating system will run on the RAM only, not from the hard disk. So this is a one kind. This is a one compute node. Is a CPU. There is a PCI slots are available, but in this PCI slots we are not placing any GPU cards, but that is always available on the server board. So that is a reason it has only one computing device, that is a primary computing device, that is a CPU. That is the reason we call it as a CPU compute node. When I'm talking about the GPU compute node, so you can see that everything is same up to here to here. You can see things are same, and there are the additionally two cards are device, two cards are connected. We call it as a GPU card. I will discuss shortly on it. So this is a secondary computing device, and this computing device is accelerating in the workload of CPU. So when this GPU card is connected on this motherboard, so we can say that it is a GPU compute node, and it is a GPU ready node. Now we had an idea that the GPU node and CPU node, but my primary focus is on what is the computing devices, right? So we have seen that there are two computing devices, CPU and GPU. Now there is whenever we read the literatures, any article, so we always come across the two term. First one is we can say that it is a multi-core devices, and another term is many core devices. So rather than reading that this part, so I will just visualize that. What is the difference between many core device and multi-core device? So CPU is known as multi-core device, first thing, because there are some less number of cores are available. But when I'm talking about the GPU, you can see that there is a huge number of cores are available, and they in actually, if you see the data sheets, you will find the scores in numbers are in thousands, 4,000, in some cases it is more than 8,000 as well. So this is a reason we call it many core device. Now I will discuss about the GPU evolution. So earlier days, when the computer was came into the existence, so we were talking about the video rendering, and in those days CPU was responsible for do the computation, a general computation as well as a video rendering computation, right? And because of these two tasks, video rendering computations is always bulkier and they are massive. So because of that, the performance of the machine of entire system was degrading. Then the idea came that why we cannot, because we know that the video rendering is a separate activity altogether, and activity is simple in nature, not highly complex in nature. So they started they developed one GPU device for video rendering workload, and other computational workload they have is given to the CPU. When this combination was tested, so performance of the system was improved drastically, and with that experiment, the GPU came into the existence as a specialized hardware for the video rendering workload or video computation acceleration. And CPU was totally free from video rendering activities. But as the time was evolved, and in those days, the specialized chip was developed for video rendering, and the architecture, pipelining architecture of video rendering was fixed. That was not programmable. But as the industry grown toward the gaming industry and other development, video rendering, development activities were happen, then some programmability has been added onto the GPU. Apart from this fixed architecture, some additional programmability feature was added, and it has given a very big boost to the gaming industry. Because of that, the new devices are coming started coming up with the programmability feature in GPU. These days we are also using the GPUs for handling the machine learning and scientific computation as well as large scale simulations, uh, wherever the massive parallelism and high throughputs are needed. So what happened here is that these days, especially when we are talking about machine learning, So many various manufacturers are talking about the specialized chip for AI. Means when we are specialized chip for AI, that means for specialized activity as well. So that is also one of the parallel development is going on these days. Now, there is a term which always the learners come across, that is GPU versus GPU. So whenever they come across these terms, they just used to get confused with what is GPU and what is GPU is. So in one sense, both are same. GPU and GPU both are same. Why this term is given the GPU? Because it has been observed that GPU cards was not only support the help in video rendering, but it is also very much powerful and suitable for handling some scientific workload as well. So that is the reason some programmability has been. So whenever I'm talking about the any workload rather than the graphic workloads, so they started calling it as a non-graphic workload, right? So because of that reason, uh, we have started calling it as a general purpose GPU computing. So again, some specialized device was developed by the various manufacturers. Those supports the graphic workload, but only 10% or 20%, remaining 80%, it supports the uh, scientific workloads. So that is the reason they started calling it as a GPU. So that for that information we have to go through the data sheets of particular GPU. Then again, there is another term we come across is a accelerator. So in beginning I mentioned that what is the meaning of accelerator. When we added the GPU along with the CPU, so CPU is a primary computing device and GPU is my secondary computing device in any server board or any computing board. So what is happening? We are just offloading some workload from the CPU to GPU. So basically is that it is just accelerating the computation. So because of that reason, we started this additional devices which helps the CPU to perform the task. We used to call it as a accelerator. And this devices always works alongside a CPU. Now there are two types of the GPU devices are available: integrated GPU and dedicated GPU. So when I'm talking about the integrated GPU, so you know that in Intel processor that is we use in laptop, right? In our laptop there is a no separate chip for the graphics. That graphic thing is inside the Intel processor only. So you can see that this blue and green color portion is indicating the CPU. This is a CPU, and this red color portion is indicating the GPU, and both are embedded on a same silicon substrate. So this kind of architecture is known as integrated GPU, and such GPU do not have a dedicated memory. They always depend on the system memory, means the RAM that is connected with the processor. And next one is a dedicated GPU. So dedicated GPU is like, I will explain you in two way. Just like in a simple terms, I will say that whenever we go to the market to buy a laptop, they always ask you that what kind of laptop do you want, multimedia laptop or general purpose laptop. So what's the difference between these two, multimedia laptop and general laptop? So if you see the difference, there is a additional they written mentioned that NVIDIA GPU or AMD GPU enabled or powered, something like this might be written and sticker is pasted on that. So thing is that it has a one integrated GPU that is available inside the processor. Apart from that, on the same motherboard, there is a additional GPU is present on the board. So this additional GPU, if you look that particular GPU carefully, so they have a some dedicated memory. They use some dedicated memory that is present in that dedicated chip of GPU. So such kind of is computing means GPU device is known as dedicated GPU. But when we comes when we look into the server board, so in on server board that kind of chip is not available. There are PCI slots are provided, and on those PCI slots such kind of cards are placed, and this card is known as dedicated GPU. And because this such kind of card has a GPU processor, along with that some RAM is available, that is known as GDDR RAM. So once the hardware is there, so after that, to make the system functional, uh, just like we need a software. So you can see here it is a hardware, and hardware we need a operating system, and operating system we need a driver. So these three things works together, right? So after that I will come from application. Suppose you are working in one domain, and you means you are developing some application, you are writing so many of codes for to solve your problems in computation. So when you are writing any application, suppose you're, what I can say, you are solving some material science problem, right? So you know the atomic structure like semiconductor, and you want it, you are adding some atoms and you are trying to convert the memory, convert the energy. For that you have written the code. But when you are writing the code, you are writing a serial code or sequential code, right? If you wanted to, because but you know that you have a CPU is a multi-core and it has a many core. Two devices are available on your infrastructure, right? So what you will do, you need a programming model for both. This you have a programming model, you wanted to use multi-core, if you wanted to many core, so programming model should be available in the software stack, so that you could use those model in the development of parallel code, right? So you need these models to develop the parallel code. When you are developing this parallel code, obviously there is the mathematics is involved, and some you need a linear algebra mathematics. They are available in the form of library, so you can call these libraries in your parallel program development along with the programming model. So this way it entire application will be developed. After that, one application is developed, then you have to compile it so that it could work on their underlying hardware. So this is a entire cycle of software stack development of any application with the help of hardware and software stack. Suppose I take example of you have a multimedia laptop, and you know that it is mentioned on your laptop like GPU, NVIDIA GPU is available. So those who have, just try whether you are using that GPU or not. So what I came across with my experience, most of the people, they purchase the multimedia laptop, but they don't know how to use those GPU. They think that it is automatically working, but it is not. It is doesn't happen. So it is up to you how to check that which GPU is being used, integrated GPU or dedicated GPU, in case you have a multimedia laptop. Now, these are standard terminologies which we use in scientific community, that is called host and device. So this is just representing the board. You can see here that what is a host system and what is a device system. So in the same motherboard, uh, the GPU, CPUs are available, and CPU along with that RAM. When we are using this CPU of that server board, so that is known as host system. And the GPU that is also connected on the same motherboard through PCI, but this system is known as device system. Means GPU card is known as device system, and this GPU would have their own memory. We call it GDDR5. Earlier days, GDDR RAM was used for GPUs, but these days we are using HBM stacked memory. This is HBM, high bandwidth memory, is a stacked memory. It is being widely used these days in the development of GPU processors. This is just I mentioned for the illustration purpose, so that you can see that the popular companies, those who manufacture the GPU cards, you can see Nvidia, AMD, and Intel, and the physical appearance of the card, one of the card they have developed, and these cards are placed on PCI slots. Now there is another very important term. Uh, I don't know, but can I take one question? If anybody discuss about what is the difference between SIMD and SIMT, any participants can put some light on it. You can just put a chat message, and one of the coordinator can read it out. Anybody can share your thoughts. Or anybody can unmute and tell me that what is the understand. They just you have to discuss their understanding. What is SIMD and what is SIMT?
Participants, anyone can unmute and share your views.
Okay, so I will explain you that what is SIMD and what is the concept of SIMT. So we generally call it in short SIMD and SIMT. Single instruction, multiple data. I think everybody knows about it. And next one is SIMT. This is a single instruction, multiple thread, right? And this is a emulation of the SIMD. So I will just explain you in this fashion, and then you can think. You should tell me what is SIMD and SIMT. So every computing device that is available at hand, that is solve any problem, real world problem. So here what I did, I have taken a two arrays. You can say data array 1 and data array 2. And I wanted to perform some operation on addition. Every element should be added by the element of second array, and result must be stored in another array. We can say it C array. So here you can see the first array is A and array B, and this is my processor section. It has a stages like I think everybody knows about that. In the processor, first data is moved from memory, means RAM, to the internal register, and then your core execution unit, that is your this green color box, we call it arithmetical logical unit, work fetch the data from the register, not from the memory. First of all, data has to come from the memory to the register, and after that ALU unit work on that, perform the operation, whatever the operation, addition, multiplication, subtraction, whatever is there. After the operation is done, it will be stored into some another register. I have taken for simplicity, so there are various way to store the register data in the register. After that, final data will be stored into the memory location. So so there are three stages. Every, if you know that, the processor also works in a pipeline stage, right? So what's the pipeline stage? The first stage is load. Second stage, you can see LD. LD is a load operation, execution unit, and store operation. So first of all, data will be bring from the memory to register, and then execution will perform its operation. When operation will be done, the final result will be stored into the memory location. So there are three stage I have considered here. So you can see that in a time t0 cycle, first element of data arrays, these two, first I'm just write it like here. First it will be fetched from the memory location, means it is going to load into the register, and other two unit, execution in unit and store unit, has nothing to do, nothing to work. And t2 cycle, what will happen, the data which we already brought from memory, it will go for the execution, where actual operation of addition will be performed. But at same time the ld was free, so it will bring the second element of the array, the second element of the array. And t2 cycle, what will happen, operation was performed successfully, and then it will go for the store operation, right? And at the same time what will happen, uh, because execution unit was free at t2 cycle, so it will be busy in performing the second operation on second element, and load operation will be busy in bringing the third element of the array. This is the third element of the array. So you can see here all units of the memory are busy and working together, right, on different data element. So this is the fashion the CPUs works. So you can see that after three clock cycles, I will say here my first element, I will get the result of my first element, that will be 3 3, and second element it will be 4 4, and in fifth cycle I will get my data is 18, and so on. It will be like that, right? This is a one way. This is a scalar processor, right? Now my data is same. I am not changing my data arrays, but what the changes I did here, I have just made my compute unit bit powerful. You can see here, I just made my machine, my compute unit bit powerful. How I made bit powerful? I have just increased the register size from 64 bit to 128 bit. So generally, I will give the one idea. These days, every processor we use is 64 bit, right? Nobody is using 32-bit processor. That is a minimum basic standard these days, 64 bit. And what I am considering, one register, one element, one data element, I will just write one E. We generally call it one element, and it occupies the 64 bit space. 64 bit space, one element, right? Then in case of double precision, generally we always calculate the performance by using the double precision. So there is a standard one element. So here that means if I go for the data array, this is a 121 is a one element of the array A, and it will occupy 64 bit space, right? That is the meaning of 64 bit processor, in case we are using the double precision. Right. So what is happening here? My register size is now increased. I'm just made it double, 128 bit and 128 bit. That means this size can accommodate two element of the array at a time. Right. So here you can see in a space and time chart. So in load operation, because my vector size is 128 bit, so I can bring the two data element at same time, and I can execute two element operation, addition operation on two data element at same time, because my ALU is also of 128 bit, and at third cycle it will be copied two data elements at same time. So you can see here in previous case I will just mention the results here as well, so that it will be easy. at, okay, so this is not T2, it should be T3. At T4 cycle, I will get, sorry, what I was getting, it was wrong. Let me erase. What I was getting here, I was getting here 3 3, and I was getting here 4 4. I was getting here 18. I was getting here 108. Right. So just compare here. In T3 cycle, you are getting only one element. T4 cycle, you are getting only one element. But in this case, because of the vector, I was able to get two elements at same cycle, right? And T4 cycle, again, I am able to get the two, process the two data element of the array at same time. This is a one. Next, same I am carrying, and what I did here, so I just mentioned here my register size is become 256. So if it is becoming 256, my ALU unit is also 256 bit. So that means at a time it can carry four elements, right? It can carry, I will just make it 2 here, and it will be 3. So what will happen? I will carry four elements at same time, right? You can see this timing charts here for understanding, as I explained already. So at a time it will carrying the four elements. So I will get the output at T3 cycle. So this will be 3 3, it will be 4, it will be 4, it will be 18, and next is 108. Right. So what is happening in a same cycle, you are getting four element as process, because you have a vectorization enabled circuits are there. If I talk about Intel processor, so you can think about, there is a SS vectorization, SSE vectorization, and then they have developed the AVX vectorization, advanced vector extension, and these days every Intel processor supports AVX. AVX means advanced vector extension, and it is name is given 512. So 512 is indicating the size of the vector register the Intel processor supports. This terminology is belongs to Intel, but other processors like AMD processor or other IBM processor also support such kind of vectorization, but naming conventions may be different. So they call it vectorization. So in general, we are saying it a vectorization technology there. So this is happening here. After that, I'm coming across the new thing. So here you can think about that. Uh, this is my compute unit, right? So I am not change the vector register size. Even I have not changed my compute unit size. But what I did, I just replicated thing on a same silicon substrate. If I have a 4, suppose here I have a 4, so that all are making 256 bit. That all are making support a 256. If all four work together, that is going to make 256. If I combine the all R1 register, it is also making a 256 bit. So that means all these four units work independently on their respective elements, all four elements. If they work together, so I will also get the answer here. They will give me 3 3, it will give me 4 4, and it will give me 18. So 18, and it will give me 108, right? So if the result point of view, if you see here and here, output is same, but architecture wise it is a difference, right? What's the difference? This environment is this architecture is not a true SIMD. Why? Because when if I wanted to use this unit, I have to launch the thread. I have to launch the thread here. So I am just forcing all these threads to work together. Only then it is giving the uh, vectorization effect. And I have a control that if I wanted to use only one core, so I will launch one thread, and if I wanted to use these two cores, then I will launch two thread. If I have wanted to launch three or four, then I have to use accordingly number of threads to work on this core. So because we are grouping the threads, and each thread is handling each data element, so this kind of is give a like single instruction multiple thread. And please note, thread is a software entity, so we are controlling it here at a thread level. So this is giving the sense of single instruction multiple thread, but this is giving the true sense of SIMD, so this is a true vectorization. So this is all the basic information about SIMT and SIMD. Now I will discuss about the anatomy of GPU of NVIDIA and Intel. Mostly I will more stress will be given on NVIDIA GPU. So I know this diagram is blurry and complex, but I will just give you some explanation about that. First, this diagram I have taken from the NVIDIA website, and this main purpose of showing this architecture to tell to show you that how these manufacturers are arranged the number of cores on a single silicon substrate. So this is the NVIDIA topology, whatever we are going to discuss right now. So you can see that at higher level, just have a look at it. So you can see there are some blocks are there everywhere, right? Uh, and some green color things are highlighting here. So green color is portion is indicating the actual compute core. Where actual means actual compute core means it has the ALU unit, right? So all these ALU units are arranged in 6 sections in this particular chosen GPU: 1, 2, 3, 4, 5, and 6. And this arrangement is called graphic processing cluster. But if you look this one, if you take any of this section, just like I am taken this section here, section 3. If you see here, there is again some grouping is here. You can see here grouping like this. See here is a grouping like this, and something small form it is like in TPC. So TPC is a texture processing cluster. So first layer is the first means controlling and division uh, architectural decomposition that GPU has that NVIDIA has followed is GPC. Within a GPC, they have again arranged the cores inside the TPC. So that we have to see here how many TPCs are there. So you can see that each GPC there are 7 TPCs are available, and these numbers can vary from GPU to GPU. After that, you know that I have highlighted here the TPC, and if you broadly, if you look carefully, within a TPC there is a 2 sections. There is a one portion, and this is another portion. So this small color I have highlighted here. This is known as SM. NVIDIA people call it as a SM. SM is a streaming multiprocessor. Right, within a TPC there are 2 SMs are there. Now this is a enlarged view of each SM, right? So you can see here it is a SM here. SM means streaming multiprocessor, and streaming multiprocessor, if you look inside again, so some arrangement in some blocks. So this is a block 1, this is a block 2, this is a block 3, this is a block 4. So NVIDIA call it as a process block. Now I will dig into the one block here. One block. Each process block has each SM has. I will just write here SM. Each SM has how many blocks? 4. I will like it as a PB, process block per SM, right? So what is inside this process block? So each process block, these are the items are available: L0 instruction, warp scheduler, dispatch unit, and register files. And after that, these are the computing units. So int 32 means integer. These units basically handle the integer data type of size 32-bit. And FP32 means this compute cores handles a floating data type of 32-bit. And this one, FP64, is a floating. It handles the data of floating type of 64-bit. Apart from these three, NVIDIA also added there the tensor core. So every GPU would have their limited number of tensor cores, but each tensor core can handle 4 by 4 matrix multiplication. Each tensor core can handle 4 by 4 multiplication. That means it can handle 16 element at the same time. Now I will go back here and I will see the information which I have discussed. So here you can see it is a how many 16 blocks in 32 is here, 16 is here, 16 is here, and 16 is here in 32. So that means per SM how many in 32 is there. So you can see that there are into where is India, there is 64 in 32 cores per SMs are available. Similarly, there are 64 FP32 core per SMs are available, and 32 FP64 per SMs are available. These are the some details you can study. Now I will look at how Intel has organized their compute core. So far I have discussed about the how NVIDIA has organized their compute cores and their terminologies we have discussed a bit. But now I will discuss how the Intel has organized their chip. So Intel used the Ponte issue. There is a one of the GPU earlier, but now I think they have stopped this Intel issue and they are coming up with another GPU architecture. So, but information is always good. So I'm just telling you that information, sharing with you people. Intel has changed their nomenclatures, means their terminology they have changed, and they have categorized their GPU in the following categories. So first one is a integrated and entry GPU. You know that there's a GPU for means laptop graphics. After that, there is a mid-range GPU they have developed, and it is also for the gaming industry. Means this GPU supports for high performance graphics, means programmable thing. And apart from that, the high performance GPU, one of the segment they have developed, and this GPU basically caters the data center and AI workload. And finally, they have developed another GPU. We call it GP GPU. I just mentioned GP GPU. So this is a category under GP GPU. Intel has given the notations like XC HPC, and this supports the HPC exascale kind of GPU. This is segments to cater. Just like Intel had developed the edge computing processor, then laptop processor, and mobile processors, and uh, server segment processor. Similarly, they have categorized their GPUs as well. So you can see that as we move from here to here, sorry, as we move from here to here, so compute capacity is also increasing, means compute power is also increasing from teraflop to petaflop. So this is a illustration how the Intel PVC modules looks like. This is a one module, and these are the supporting circuitry. You can see this is the actual chip, and this is the entire module. So Intel people call it as a OCP accelerator module, and OCP is a Open Compute Project. This is a just naming conventions. OCP is an open project, means they have taken a standards from Open Compute projects in the development of this GPU. Now they are talking about the subsystem, means the subsystem is made from the modules. So here you can see this is the entire subsystem, and in this subsystem we can add attached four modules. So you can see module 1, module 2, and module 3, and these four modules are the GPU, Intel GPU module. So because of that they call it X4 subsystem, and all these modules are connected with the XC links. XC links means Intel has developed their own communication links. So these four modules are connected with those links. Now this is a entire compute system. So here you can see here it is a CPU. There are two CPUs are available, and after that they are supporting circuitries, cooling circuitries are available, power circuitries are available, but my main focus is on this 4x subsystem. So this is a entire GPU compute model that is connected on this GPU compute node developed by Intel. Now I will talk about the architecture. So I will two stack I will not discuss, but first of all I will discuss this uh, single stack. So here you can see that just like in a NVIDIA GPU, they have arranged their cores. So here also this course is representing in this black color boxes. I'll show illustrate that you in a expanded manner. So here you can see it looks like there are four such blocks, 1, 2, 3, and block. And NVIDIA people is used to call it as a for their blocks GPC, but Intel people call it as a XC slice. So these are naming conventions. Intel people call it as a XC HPC slice. So what you have to think, there are four arrangement of cores are in a form of blocks, just like NVIDIA GPU. There are four blocks, such blocks. So this is a enlarged view of one each block. In each card there was a two there's a four XC blocks on a GPU, but here you can see the enlarged view of each XC slice. So if you see the in XC slice, so you can see there is arrangement of XC cores. How many XC cores are there in? That is a 16 XC cores are available, right? Now I will move deeper into what is inside the XC cores. So if I select one of the XE cores, you can find it as a vector engine, and there is a XMX. So how you can map with the Intel, map with the NVIDIA GPU. So NVIDIA GPUs are totally, there is no vector. So they use the SMs, arrangement of SMs, number of cores. So they are grouped the number of cores within SM. Within, you can say it is a process blocks where cores are arranged. So there, NVIDIA GPUs does not support the true SIMD. And again, I'm specifying and stressing this point. NVIDIA GPUs are SIMD in nature. They are not true SIMD. But when I'm talking about the Intel GPU, this is a vector engine, and the vector size is 512. They are true vector, and this vector engine is an actual compute unit in Intel GPU. In NVIDIA GPU, we have talked about the tensor core, and the same operation in Intel is performing by this XMX unit, XC matrix extension unit. So thing is same, operation is same. It also support the matrix multiplication. Tensor core also support the matrix multiplication, but and naming conventions and architecture is bit different from each other for each other. So now these terminologies, you can see that the earlier days Intel used, I think we have studied in 8085 and 8086 processor. So that time they used to call it as a execution unit, and this is for a matrix they used to call systolic unit. But nowadays, what they are calling it execution unit, they are calling it as a vector engine. For matrix engine, they are calling it as a matrix engine, and NVIDIA is calling it as a tensor. Now, sub slices arrangement of cores, vector engines in a one group, we call it as XE core, and now this is called XE slice, and then last will be the stack. So these are the Intel's new terminology, and generically we call it vector engine, matrix engine, slice, and stack. And these are the new abbreviations. You can find these abbreviations in many literatures, even NVIDIA document, sorry, Intel document as well. So I'm skipping this calculation because of the timing constraints. So now you have to understand there are two things for every programming. There's a hardware terminologies as well as the software terminologies. So hardware terminologies, I have discussed only these two things, NVIDIA and Intel GPU. So they are the GPUs. There are different arrangements: graphic cluster, processing cluster, texture processing cluster. Intel GPUs are arranging it is a slice. We call it XE slice, and then it is a streaming multiprocessor, NVIDIA people call it, and we are calling it a vector core, XE core we used to call it. NVIDIA we are call it as CUDA cores or compute cores in generic, but Intel people is calling it as a vector engine. So these are the hardware naming terminologies which is used by both NVIDIA and Intel. But when we have to develop the program, we have to write the program for this underlying GPU. So they also support some software terminologies as well. So in software terminology, they use a thread block, and the same thing we call it as a GPU. Sorry, group. Warp is known as subgroup. Thread is known as work item, and emulated with SIMD warp. That is a emulated version of uh, SIMD, as I mentioned earlier, but it is not a true SIMD. Is an emulated version of the SIMD, but Intel is a true SIMD in nature. Now we will do how the calculation compute capacity is calculated for NVIDIA GPU. So you can see here is that uh, GPC, you can see the count. You can take any of the example, like there is a 8 GPCs are available, and there are per SMs how many TPCs are available, and there is a term SM per TPC, how many, this is fixed for all. And my main focus is that how many SMs are available per GPC per GPU. So this is the first parameter I am always interested to calculate. And then the second parameter I am interested to calculate is that how many FP32 cores are available per GPU, this second one, and how many 64 cores are available per GPU. So once I know the number of SMs, and I know that how many FP32 cores are available per SM, and how many 64 cores are available per SM, so I can calculate the number of cores FP32, FP64 that is available per GPU. So here another important thing is this one. So you can see here, this is talking about the tensor cores per SM that is available. So NVIDIA 100 card has a 8 tensor cores, NVIDIA A100 and V100. So A100 has a 4 tensor cores. So total tensor cores you can compute is like 672 and 512 that is available on per GPU. This is the way, this is the formula to calculate the theoretical peak performance of NVIDIA GPU. So what are the parameters should be known? So you must be known SM counts, streaming multiprocessor, CUDA cores, whether it is FP32 or INT32 or FP64. This is the thing, like you have to always it multiplied by 2 factor, because every unit supports FMA, fuse, multiply, and addition, and these two units work together, means they can perform addition and multiplication simultaneously. So it at the same clock cycle. So that is the reason theoretically we always consider it as a 2. And then the GPU frequency, the frequency, operating frequency of the GPU cards. You can see here the calculation I did. So number of cores I wanted to calculate for FP32 cores. So I have taken, it is 512 from this table, and I know the frequency is 1530 megahertz, so 1.5 gigahertz, and I mentioned it is 2. By default it is 2 because of FMA, and if you multiply you will get around 15.7 teraflop per second for FP32, and you can compare this with this value. That this values I have taken from the specification sheet of that GPU. So it is exactly matching 15.7 teraflop. This is a theoretical peak that is given in the specification sheet of GPU. Similarly, I have given some idea about the how you can calculate the tensor core calculation you can do. So some table is given here in green color. So you can see here Volta, Turing, A100 and Ampere, and number of CUDA cores are available and tensor cores are available. These are the specification I also got from the specification sheet of the GPU. You can see the tensor cores, that's the main point, is that tensor core can handle 4 into 4 matrix multiplication in one clock cycle. So when I am talking about the 4 into 4, that means 4 into 4, 2 matrix, 4 into 4, and it always result another 4 into 4 matrix. So there is some variation always comes in architecture. That is the reason I'm stressing on this point of multiplication. When one operation is performed, there is always a 4 multiplication operation and 3 addition operation, and these are overlapped. So means they are hiding the latencies of each other. So that is the reason one element computation of 4 into 4 matrix multiplication always requires 4 flop operations. So in matrix multiplication we need a there are 16 elements. So how many flops is required? We can multiply it by 4. So 64 flops is required for 4 into 4 matrix element. So now this is a formula for tensor core, number of tensor cores that is available, flop for the uh, matrix, 4 into 4 matrix, and frequency, and then it should be multiplied by 2 FMA. So here you can see that 640 value is always mentioned in the data sheet. You can, if you check, you want to go back here, 640 here, right? And then flop for matrix, so you know that it is 64, and then frequency, you know that the GPU card is 1.53 gigahertz, and FMA. So when you calculate, it will comes across 125 teraflop. So if you check with that how the tensor core performance is given in a specification sheet, you can find it like that. So you can think of it now how you can do the calculation of all this. And after that, when you do this, you can run your models and you can check whether you are getting the nearby performance or not. Same thing I did for A100 card. So same operations are here, same parameters I have calculated here. So only thing is important, why I am stressing, why I always study this portion of data sheet for any GPU, is that tensor core handle 4 into 4 matrix multiplication in one clock cycle. That is fixed. But what they did, they extended to 8 into 8 matrix multiplication for FP32 and tensor 4. So that is the another important point. They are extended instead of 4 into 4, they have extended it for 8 into 8 matrix multiplication in case of A100 tensor card. Now, there are two types of GPU memory they are used. First is GDDR, and another one is HMB. So GDDR is almost outdated these days. So these days we use HBM memory. So some difference in calculation I mentioned here. So that is a view of one card I have taken from NVIDIA sites, and you can see here is that this chip 1, chip 2, and this is a GPU card. This is a GPU. This is entire card with supporting circuitry, and these are the memory chips. These are the 6 memory chips. They are connected, and these two modules are blank, so they can connect more memory chips here. So because of that reason, graphic card with same GPU architecture are available, but different memory configurations you may find in the market with different cost. So this is a standard formula to calculate the theoretical memory bandwidth. So first thing we have to calculate is the total memory width. So how you can calculate the total memory width? Interface width per chip and number of chips on the GPU card. So that means this chip has a fixed number of interface. Suppose I am considering it as for example, I am just considering it as 16. My bus size for this chip is 16. Then we have to multiply with 6 chips. So that will become my uh, interface width. And then interface width will be divided by 8 because 8 is indicating the data bus size. So my data size is always in 8-bit. So that is the reason we divide it, and it should be multiplied by the base clock speed and data rate. And after that, there's two parameters are carefully we have to consider by reading in detail about that memory. First one, it is only for GDDR case, and data pumping technique and PMA4 signaling. Whether the chosen GDDR supports what kind of data pumping technique it supports and what kind of PMA signaling it supports. So these two parameter we have to be taken care in the calculation of theoretical memory bandwidth. Here is a table, one table I have just shown you, and I have taken three different GPU cards, and in three GPU cards, what kind of GDDR memory they are used, I have mentioned here. Right, this is a chip number, memory chip number, and bus interface per chip. I have taken it is 32, 32, 32. There's no change in bus interface width, but number of chips are changing 6, 8, and 10. You know that we have to multiply these two. And another important thing is that data rate associated with this memory chip. That is a 2 DDR double data rate, and GDDR RX supports a 4 QDR quad data rate, and GDDR R6X that is also supports the QD4 QDR. 4 means that value data rate is 4 means that is a QDR quad data rate. So that three parameters you got it. And then operation per cycle means pumping technique it supports. So pumping technique means it is a 2, 2, and 2 we have considered here. Next parameter is a signaling scheme. In this memory GDDR5 they are using the okay, so that should be not NZR, it should be NRZ, non return to 0 bit. So whenever we use this kind of signaling, data information will carry in 1 bit. So when we are using the PMA4, so each signal will carry 2 bit of information. So that is a difference also comes in calculation of theoretical uh, bandwidth. So clock speed that is given in a specification sheet, this value is a product of these two, and then we just multiply all these values, you will get your answers here. You can find calculate it later on. To get a more information, you can visit the websites for this uh, GPU cards and do the calculation again. Next step which we are using these days is a high memory bandwidth calculation. um, so so whenever the time will come, please let me know. uh, High memory bandwidth calculation, so these are the stack memory chips are widely being used these days. So this bus interface width is very high. You can see we are using 1096 bit for HMB2, and a new chip that is compare that we are attached in A100 card, that memory width is 5120 bit. So simple calculation, multiplied divide by 8, multiplied by the frequency, multiplied by the 2 for double data rate. So you will simply calculate the bandwidth of the HMB memories. So these are the all about the different computing architectures. If you have any questions, you can ask. It's open for discussion.
Participants, you can ask your questions and doubts. Are there any queries from the participants?
Participants can unmute and ask their any questions or any doubt they have, because I think next session is also in line, right?
Yes, sir. Yes, sir.
Okay, so I think what is the time now? It is 5:02, so I will log out so that next speaker can take up.
Sir, just
Wait,
wait.
wait for a while, sir.
Pardon?
Wait for a while, sir.
Okay.
Can I share my screen?
Yeah, I will stop sharing my screen.
Yeah. First and foremost, we extend our heartfelt thanks to
Ma'am,
Dr.
screen is
Vamshi.
not visible.
Wait, wait. I hope it is visible now. Is
Yeah,
my
yes.
screen? Thank you. First of all, we extend our heartfelt thanks to Dr. Vamshi Krishna Sabbi sir for sharing his valuable insights into the emerging trends in hybrid computing. His clear explanations have provided us with a better grasp of how this blend of technologies is shaping the future of computation. Sir, please accept our virtual token of appreciation. Thank you so much. We would
Thank you.
also like, yes, sir.
Thank you.
We would also like to acknowledge and express our thanks to all the attendees. Thank you all. I request all the participants to be in the same meet for the next session. Once again, thank you so much, sir.
Thank you, sir.
Thank you. Thank you all.
Thank you, sir.